So we will now do a final modification to our A-star algorithm. And this is due to the following observation. Say you want to go from the start to this goal, and you're driving on a parking lot, for example. And so here's another parked car, and here's yet another car. Then as you see, and as we'd expect from our algorithm, those cars won't change the trajectory at all, because our trajectory is only changed if it actually hits one of those obstacles. But in real life, it would be more natural that we get around this obstacle at a certain distance, and also we try to get around this obstacle at a certain distance, so that in general small distances to obstacles are avoided. The same is true, of course, if this is some entrance where you would have to pass through, and it looks like this. Then of course you would expect that the trajectory tries to drive in between those obstacles instead of almost scratching one of these while there is lots of space on the other side. So how can we achieve this? And we will use a potential function. And let me explain this to you using a real-world example. So say you go hiking in the mountains, but actually you're not a friend of hiking in the mountains, but are somehow forced by your friends or whatsoever. And so they tell you, we will hike from start to goal in this mountain area. And so you take a map and look at the contour lines, and you see, here's one mountain, and there's another mountain. And so you tell your friends, as you know, I don't like hiking in the mountains, so going from S to G, I will just go along this path down in the valley, and I will never go above sea level. So that's good for me. So unfortunately your friends tell you that you didn't look carefully enough at the contour lines, and although S is at sea level and G is at sea level as well, there's additional contour lines in the map here. Like this. So say this is the 50-meter contour line, 100, 150, 200, 250, and 300. So it is impossible to go from S to G when you want to pass between those two mountains and you want to stay at sea level. So you tell your friends, okay, so if I have to stay at sea level, I'll just go around the two mountains. But then they tell you, well, this would be a huge detour. And so you say, I would be willing to go a little bit above sea level if this avoids a huge detour. And so your friends ask, well, how much of a detour? That's a pretty inexact statement. Now, being an engineer, you of course are able to come up with a definition that is exact. So you say, these are all the levels I'm able to make. So I love sea level. And here, I will never ever go at a height of 250 meters or higher. So this here is an absolute no-go area. And below that, I will use the following cost function. Well, moving one step at sea level costs me unit cost because of the amount of work of going forward for one step. And from there on, it gets harder and harder for me, increasing linearly with the height above sea level. Right? So say here the additional cost is something around 4, so the overall cost would be 5. So you would say making one step at sea level costs me a unit cost, but making one step at 254 meters above sea level will cost me 5 unit costs. And so here it is, the perfect specification. It is of course unclear if your friends will ever take you on this hike, but nevertheless it is a perfect specification. So which means that here at 255 meters and above, there is the absolute no-go areas for you. And since these no-go areas do not block the path from start to goal entirely, you can take part in the hiking. And in fact, this might be a possible outcome for the lowest cost path. And note again, this cost function is designed so that when you walk at a certain height, you incur this cost for every unit step you do. So in real life, this would mean, for example, that you suffer when you have to walk in thin air. Whereas one could think of other cost functions which only add to the cost if your step actually goes uphill, but do not add any cost if you walk horizontally or go downhill. So in our case, every step adds to the cost. Now, how does this fit with our algorithm? Well, as you can imagine, these values were chosen deliberately. So in our obstacles array, we so far used the values 0 for free space and 255 for obstacle, and we had no value in between. Now the user interface will generate also values in between. So for one part, the algorithm stays the same. When it encounters a value of 255, it will not enter the obstacle. But if the value is smaller than 255, then it will add a value, and the added value will be approximately between 0 and 4. And since we know that the value of obstacles is between 0 and 254, we will use obstacles divided by 64, right? So for 256, this would be 4. So it is slightly below 4 for 254. Now let's see what parts of the code have to be modified. And you have to modify only a single line of code, right? So when you compute the cost, which means the new cost and the new total cost, you have to add to both of them the value of obstacles divided by 64. And you can, of course, experiment with other values here, which then change the behavior of the algorithm. But still make sure that you avoid obstacles altogether if the obstacle value is 255. And astonishingly, that's the only modification you'll have to do. Now, before you implement this, let me show you some of the very cool results you can obtain. So let's start here and go to here. And you can now also switch off the visited nodes to make the result clearer. Now let's draw an obstacle. And as soon as you release the mouse, it will now show you the potential function in blue. So the red area is still the absolute no-go area, whereas the blue area just adds cost to the path. Now this blue area is computed by using a distance transform. So the value decreases linearly with the distance to the red area. So now if I start to touch the path with non-zero values of the potential function, the path will try to avoid the blue area. However, if there is a second obstacle coming from above, then as soon as this also hits my path, you can notice that the path tries to go exactly in between those two obstacles. So that is the actual behavior we intended to have. Now let's do the parking lot example that we discussed earlier. So you go from here to there, and there is a large parked car, so it will avoid this. And there is another large parked car, so it will avoid this as well. So this is a more real-world trajectory than what we would get if there is no potential function. And indeed, you can switch it off by clicking here. You see, without the potential function, you still get the straight line. And with the potential function, it will avoid passing close to the obstacles. Let me show you something else. So say again, you have this wall coming from below, and so it avoids the wall. And you also have this wall coming from above, and so it goes in between. But now as those walls get closer, it will suddenly get around the entire structure. And this may be unusual at first sight, but remember, in the hiking example, it was also an option to get around the entire area of mountains just to avoid costs. So it's just a trade-off between this detour and the costs which you accumulate when going through these two obstacles. And if this gets longer here, then it reaches a point where it again uses the opening between the two obstacles. Now let me make another nice example. Say you're driving here along the street. So this is the side of the street which you can't pass, and you're looking for a parking lot. And so you see, here's a number of parked cars in one row. Here's a second row. There's an empty spot. And here's the next row. Right, so you want to go from here to this empty spot. And as you drive along here, you suddenly see, well, here's the entrance to the parking lot, so you can go over here. And so your path planner immediately gives you a good solution. If you switch off the potential function, you see that this absolutely doesn't make sense, but this here looks quite realistic. So if there is a huge truck blocking your way here, maybe heading even for your parking space, then your plan will give you even a way to kind of overtake this guy and be the first in that spot. At least if you have a car that manages to go between those two other cars. In the end, let me show you that you can also draw some kind of mountains and see the effect of this on your planned path. So if the mountains are as dense as that, it will get around them. If they are less dense, it will find a path between them. And of course, it will also find a path in between. If there is no other options. You can also switch on the visited nodes, and so you will notice how the search cost gets higher. So here there are more nodes expanded when the non-zero values of the potential function start to touch the shortest path. Now if I have pressure from above, you will see the trade-off very nicely between going through this narrow passage and going around the entire structure. And this is actually a real-world problem because the potential function may actually block narrow solutions, which are nonetheless good solutions, by forcing a detour due to excessive costs. So now go ahead and program this single line of code.